See here, this is the launch of the PSLV for that particular one, where we had both the Cartosat 2 satellite as well as the launching from the Sriharikota launch complex. See what happens is in this particular launch, every launch what they do is they place the cameras at different locations, so that each person has got different viewpoints to be seen. So accordingly you see that one is from one angle, so now he sees from a different angle they have taken. You see just is about to take off. See, there's already the ignition has started, and after the strap-ons they ignite, then they take off, because you require a large thrust to take off. See here, now it takes off. So this is from caught from a different camera. You can see the way it fires and then takes off. That from this one now from another angle. See, each person, as I told, is interested in different the studies. So they will, from the different cameras, they will have the study. So here you can see this has started firing, just started. But after the strap-on they get ignited, it will take off. This is a long shot, because in the other ones we were not able to see how the whole vehicle is moving. Here you get the whole vehicle idea as to how it has moved. This is a launch tower on which it is held.
Is it the actual speed or is it in slow motion, this flipping?
Which one? No, that speed they can adjust. Okay. This one you can adjust. See, it depends on what sort of viewing you want, See, this is meant for study. Once the video is taken, then you generate the way you want. That can be done. That speed and other things you can adjust. See, a person who is interested to know what really has happened, he wants to know how this bloom has taken place. He wants to study, he will make it even this slower than this. See, once the basic video is available, you can play around. Because nowadays, the technology is so fantastic that you can do all the things, isn't it? Once you have the basic video, you can do whatever you want, you can patch up, you can do this. See, the man, he wants to know how this has flown in the other direction. Earlier, we were looking at the full vehicle. Here, we are looking at the plume which is coming out on this direction. In the other case, we found when exactly is the strap-on getting on. See, different people have got, that is why the cameras are fixed at different directions for various studies. I think now it will stop. So this carried the Cartosat 2 satellite and this one, SRE, that is the Satellite Recovery Payload Experiment, because we wanted to make sure that we can get back this also. Not only we can launch the satellite, we can get back. So here, that is the next video in this one. Yeah. SRE recovery. This is what I was telling you that time. See, we have already launched the satellite along with us. After that, it had some experiments given by some experimenters from various places in India. The experiments were there. After a few days, we wanted to bring it down. So it was brought down to India. So here we see now we are already waiting in near Madras. There is a place called Ennur. This off Madras, where we can see this. You have to switch off the light if you want to see. Okay, this is okay. So we have taken help from Navy and other Coast Guard experts who can take care of this awareness. See, this is one of the helicopters which wanted to spot this one. See, this is another aircraft. That was that. Plus, we wanted to one more aircraft, and this is the aircraft which really spotted the one after having splashed. You see, this is the spacecraft. This is spacecraft along with that flotation system in state. So this has spotted, and immediately the ship moved to that location to get the. This is the one. This is the spacecraft, and this is the flotation system. On this flotation system, you can see these are the antennas embedded on this. See, this is collapsed, so what we did is we made like a tape and then directly fixed onto that. Here the Coast Guard is just checking to find out if there is any this thing, some gas, some gas or some of the liquids which comes from this, if it is poisonous, it should not explode as soon as you go nearby. So that some testing is doing that. See, we have NS2 there. So that has NS2, N2H4, hydrogen. Not hydrogen, sorry, in this particular case we have a bipropellant, that is the MMH, that is monomethyl hydrogen and nitrogen tetroxide, N2O4. So now it is there, now they are coming close to that. See, this is black in color because they are all specialized thermal types which can withstand very high temperatures of more than 1000 degrees when it was coming for re-entry. So we wanted to make sure that after it comes back, whether the systems are intact or it can, and so that this is this thing for re-entry vehicles. So now he has tested that the system is safe, and then he has now hooked on to his buoy and then bringing it to the master ship. See, here we had a beacon. That beacon signal could be seen, could be detected. So here you can see that full Coast Guard, they are waiting to retrieve this back to this side. So here we were wondering how to fix the antennas because it is getting collapsed. So we thought the only best method is to use a very thin antenna and then with a tape, so that even if collapse, nothing happens to that, and you this thing when it deploys fully bloated, it nicely takes the form and it can get the position. See here, these are the solar panels. This was initially collapsed and now during flotation time it opens out. So now the Coast Guard, they are fixing the location with which you can handling system so that it
opens out once it reaches the sea. When does it open out?
There are timing meant for it. Timing, different time.
Okay.
For different flotation systems, we have a photo that timing diagram. Yeah, when it comes just before splash. See, we don't want it to sink, So just before that, so now the whole thing is getting directly fixed onto the spacecraft container. So because at this place we cannot do any testing. So what we do is we thought we will from here. This is a full. You can see the whole spacecraft and our microchip belt array is somewhere here. So this full thing is being taken in a container. This is a spacecraft container, and then it was taken to Sriharikota. After Sriharikota's this thing is over, it came to Bangalore for us to do the full test, and we found most of the water has not entered, but many of the systems after you drain the water, they were still working. This is our chairman, Mr. Madhavan Nayak. He was there in this Ennur port to receive this update. He is director of SAR, Sriharikota. That is how we retrieved the satellite. This is only to make sure that not only you can launch the satellite, you can also bring things back. And in Moon Impact Probe, we had given the satellite got the impact probe got separated from the satellite, came and it took about 25 minutes flight, and came and collided on a Shackleton crater, and that this thing, when it came in this full part, it took a lot of pictures of the moon, and it was transmitted to the Earth, and that transmission also was done using the various communication systems which we used. So there, of course, we see only those which one it is? See, it's launched from a different this thing, from a long distance. When you can see that. This is what we will see in the naked eye like this. You can even see hear the clapping sound from persons who are viewing that. See, the illumination condition has been reasonably good. Otherwise, you cannot see that much.
What sort of camera they are using? They are able to capture.
Yeah, very high speed this thing, and at different locations. You see, they locate the camera at different locations. Not only in the slightly away from Sriharikota, also they locate number of cameras, and each of them are kept in such heights. And it is fixed and gone because nobody can go anywhere nearby because the safety will not allow you to do any. So everything is set and then the camera control is at one place. For video camera, actually wherever they are fixing, they are very well secured. That is done. But for them, the shock is very short time. See, from the launch pad to that, there will be some good distance, and that distance, the shock which will create on that is much less than an antenna system which is already fixed onto this at this place. So that will experience much more vibration than the one which is there outside. Outside is only a secondary effect. And then there are safety limits. No, you cannot stand anywhere nearby. Normally a minimum of 3 to 4 kilometer distance is specified for even viewing. Even for viewing you can have a minimum 3 to 4 kilometers distance. See, sometimes the cloud is there, you will not be able to see clearly. In some cases we found that almost after launch, in no time it gets into the cloud, you will not see anything. But everything otherwise is due to from your data only you can find out.
Are there any specific timings in the day when launches take place, or it is?
Yeah, definitely there are timings because if you take our country, around 10:30 is the time where the whole this thing country is well illuminated. If you go early, suppose you want to image around 8:30 in the morning. Some places in the north they are not having sufficient north, especially eastern side. You will find in winter season they are not well illuminated at about 8:30. Whereas southern side it is okay. So to make sure that everywhere when you take the imaging, because the path will come from say east to west, north to south. When you take that path at different locations, it should not be different. No? So what we do is we select the time. So according to the time, the launch time is fixed. And launch time, and you cannot exactly give, you should give them some launch window. For some small bug may be there here and there, for which some 5-10 minutes difference in launches. So again you can see that suddenly change in the plume which you saw is because of the jettisoning of the this thing. And from the core engine, there are 6 strap-ons. The strap-ons they will get separated out because their job is over. So as soon as the job is over, they get shed. They will go off so that the weight of the rocket will come down. So that is what we will see. See what happens, a lot of vegetation and other things they will get burned as soon as this goes, if it is nearby. But this one which you see here is slightly far off, so that you really don't see that. It's all different angles which is taken. No problem, you can stop. Because sometimes you see this has been clearer than that. See the different cameras which they use. See, you see this is much more clearer than the earlier one which you saw.
What about the speed of the yarn?
Huh?
The speed of the
Which one? Camera?
The speed of the yarn.
The speed of the vehicle.
Vehicle, that will vary depending on the initial thrust. Initially you find it goes very slowly.
How we can find the speed?
That they can. We have a radar. With which we can find out all the details. There is a radar with which they see there is a C-band radar which is there existing in in Sherikota, where they will do in both modes. They will do, there are two modes. One mode is called a skin mode, where you can directly go to the target and comes back. With that return they can find out. Second thing is, if it is going far beyond that, they will have a transponder mode, which they will find out all the details. Chandrayaan spacecraft, I was talking about the data transmission from the spacecraft to the ground. Some of this thing you have seen on the phased arrays earlier. Here this is not a phased array, it is a dual gimbal antenna. In the earlier case it was an electronic phased array antenna. This is a dual gimbal antenna where the antenna is fixed. Here everything is fixed. This particular antenna produces the required beam, and that beam is rotated depending on the area of interest. It will point exactly to that station. See, if the spacecraft is there, from there this is the station. At one particular position it is required, at other times it will change. So the gimballing mechanism will rotate in such a way that it will continuously point to the earth. In the earlier case, what we found in active phased array, it is being done electronically. Now it will be done mechanically, but the antenna is separate, and the antenna has got this parabolic dish which is having a system. This is the actual system which has gone in the this. So for this, if you take this, you can see the plot. See this one, this is another view of the same thing. You can see for the how much of thermal design aspects you have to take care. See here, you saw that the back side some covers, they are all called MLA cover. There is a multi-layer insulation cover. Multi-layer insulations are used to make sure the temperature of the antenna is maintained within the specific range. And here in front, apart from that, there is another sheet, is a special protective shield which is used. So this plus that together forms the total thermal design. This is apart from our mechanical and electrical design. There is a special thermal design. Otherwise, the antenna surface will get distorted and the beam will get off. Beam will go off from here. See here how the pattern is taken. See, the antenna is there. Now we have to take the pattern. How do you take the pattern? This whole antenna is taken into a compact test facility, compact antenna test facility, and then we know what are the cuts required. So accordingly, these cuts are all specified and the frequencies keep fixed. And all those frequencies and other things, once you load into the computer and then start the full thing, the whole range, it completely makes the pattern. You see, to make sure that your system is working very well, you overlay one on top of the other. So you see how well it is done. You can see here. Here, if you see what is written here, you see this is one is written here, RFC or LFC polarization, and what is the what are the other details like frequency and all those things are written here. And you find that the pattern is very good, and this is the main copolar pattern, and this is the cross polar pattern. The cross polar is about at this main area of interest. This is our area of interest. It is all way better than 30 dB. In some cases, it's even 40 dB. So this is the area of interest for us. No? These areas are not of interest because they will go completely out of the range. When you are talking from this one to all the way from Loon, Chandrayaan to this, these areas are not of interest. Only this will be of interest to us directly coming. And this side, even cross pole is very good. This is the plot for the other one plane, and this is the plot in the other plane. This is nearly, you can see, so very symmetric. Because see what we have to do is for some mechanical purpose, the antenna which is there, the edge was slightly chamfered, because when you rotate that full antenna, we found that it was fouling with some other element in the spacecraft. So it was necessary for us to slightly slice all those things. They will in spacecraft technology, what they will do is, depending on the configuration and other things, we may have to do, like people they say we have to cut corners. We really had to cut the corner to get the actual thing fixed. Otherwise, in the movement, it was touching some area which they cannot move that element out. So it was necessary for us to do that cut, and once you do that, we want to make sure that everything is fine. We know that, see, that antenna towards the edge, if you cut a little bit, the effect of that, because it will not be much, because the illumination towards the edge from the feed is less. So that way there won't be any difficulty. So that's why we made a measurement and it was very nice. Yeah, that we have shown. See, this is the full antenna. Next one. These two they are shown. This. Yeah. See, this one in the same say antenna. This one we were talking about this. This is our next one. This board, no? This one. This also over. See here, in MIP antenna we used one inverted F antenna because between the moon impact probe and the spacecraft there was some communication required, and that was at UHF. So because it is in UHF, so we used a inverted F antenna. So that inverted F antenna is being tested using the this is for impedance and other measurements are being carried out in this. But this is a very important element which has come up recently. We have seen a lot of publications from various people, and it has found an application in our spacecraft also. Because it is in UHF, we found it was one of the best. So with this, we have completely used it. The moon impact probe was taken off and then landed, etc. And we had a full data of all the 25 minutes of its travel, and this has performed very well. In fact, in one of the recent IEEE International Symposium, this system got the best paper award. Because right from conception onwards until the last thing was over, right? Conception, design, development, testing, then actual operation, everything was over this. See, in most of the places you will find either a design only is available, or only simulation is available, or only some experimental results are available. Here A to Z, everything was available. So, and it was presented in that way, this one. So they got a prize also in this. I saw it. See this, what I want to show is this quadrilateral helix which I told. These are the actual elements we have used in Chandrayaan. This full this thing, whatever I am showing, everything is virtual. So this quadrilateral helix which I was showing, this is how they have quadrilateral helix as it is. It looks like that. Everything we had, the previous photograph had showed with the radon. So here you can see this is the PCB on which these elements are fixed here. You can see elements are exactly etched. So on a single PCB you etch as per requirement, then roll it off and then bond it, and then the hold is on a small circular aluminum plate, and that aluminum plate you can have some small extension with which you can nicely hold it. So this, and then this is the epoxy. This is a H54 epoxy is made by a specific company called Epotec Epoxy, and this is a qualified material of NASA. So this is material, and these are the four, and this is the feeding network. This is a feed network which will give you the required amplitude and phase for all the elements, and then finally there is a connector out at the base with which you can take it out. So here there is 4 elements, 2 LCP, you have 2 LCP, 2 RCP. You can see this is wound in this direction, that is wound in this direction. You can see the difference, no? This is in this direction, this is in this direction. Here also this is in this direction, that is in another direction. So LCP, RCP both are available here, and this is the exact unit which is used in this band. This is the anechoic chamber, no, where we have made the measurement. You see the antenna is getting fixed. Not anechoic, in fact it is a compact antenna test facility where we have mounted the full antenna and getting ready for the test. After this test only we got that actual patterns. So this one, after the antenna which we saw here, now they are fully assembled. This is a radar, and this is the connector, and then this is the mounting structure, mounting boom, and then this is directly fixed onto this, and then see how neatly the cables are coming out. This actually is a semi-rigid cable because we wanted to reduce the loss, and in semi-rigid cables, the loss is minimum. So this is called 0.141 inch semi-rigid cable, and then there are connectors are also special crimped connectors where there are no solder joints. See, we want to avoid solder joints, so that solder joint sometimes becomes unreliable, absolute material, and this gives you the required phasing. See, this is also used in MIP. See, one is required on the spacecraft side, one is required on the antenna, on the MIP payload side. So both these things were used. So this you can see this one, and this is a network, and this finally it will be closed, and then from this you can take the output. See, always on the virgin connector you have to fix a connector saver. It's called a connector saver, so that the virgin connector of the antenna, this one doesn't go bad. Otherwise what happens is a few times when you use it, the connector pin goes bad. So the reliability of the system comes down. To make sure that you don't use this connector too many times, you put a connector saver. Connector saver means only once you connect. Any number of times you want to use this point. After this is over, you remove this, and finally when you connect it to the spacecraft, that time only you fix it and connect it. So that you don't utilize that panel connector which is used for a number of times for all your exploitation. So that is one of the rules which you should really follow when you do the measurements. So this is also the same thing that is with the boom, is without the boom. See, one is downlink and then one is for uplink. Because here S-band size is similar. Because they are all only very close to 2 to 2.5. Sizes are not much different. Whereas C-band the element was very, very small. And that too for uplink is 6.4 gigahertz, downlink is 4.2. So the sizes are much different as we saw in the earlier in the morning. So here I told you that chamfering, no? You see the chamfering here. And this is the feed. This is a corrugated structure. This is a feed. And this is a host of, this itself is a big job. This dual depolling, there is a control electronics, there is a mechanical element which to move both azimuth motor, elevation motor. So this itself is a very big job. Actually we have a separate group called mechanism group who does this mechanical part. And for controlling that, there is a separate control electronics which is done by your control group. So it's the height, and then all these thermal designs are done by different thermal group. All electrical design principle testing, and the total, of course, the responsibility to the communication engineer. Then all this fabrication of this CFRP, that is carbon reinforced plastics, they were all done in our center at Trivandrum. So there are so many agencies involved to make this antenna. And this is the structural harness which was mounted onto this spacecraft. So you can see the amount of mechanical work, mechanical, electrical, thermal, everybody is involved for you to get this full antenna. The volumetric model of the MIP structure on which it was fixed, and then they have made the measurement. This is being done at antenna test facility in the outdoor range at Trivandrum. You can see the sea on the other side. That is the western side. The sea is on the other side. Okay. This is only you saw that measurement being done. So this is all the patterns which they have got. See, this is the pattern, and what is required is only the small portion. Other portions we are not interested, because when it moves, the small angle which it will step towards the spacecraft is very less. When it moves out, during that small portion only there is a signal has to come. So you don't require that much of a wide angle, but this is more than sufficient. So this has been done in this place. Yeah. So this is the quadrifield helix pattern. You can see, as we have shown earlier, this is also at this place. You can see what is this is for Chandrayaan project, and this is the levels for different frequency bands. It is written here. So this is the actual antenna pattern which we have received, which we have made. Actually, in this particular, why we showed is this is slightly sharper than the earlier one which we had, because in this what we have done is we have used two quadrifield helices, one on one side and another on the opposite side. So we wanted to slightly shrink the antenna and get it, so that the interference zone is less. So that's why you can see here it is tapering off quite fast. Compared to the morning whatever I showed, it was coming almost up to this much and coming. So here we have slightly shrunk this, so that if you have another antenna of almost this size, that would do the job. For Chandrayaan we wanted to have a much wider coverage, so that is why we have made like this in this. See here, I was talking about the imaging systems. You see how the imaging systems are seen. See here, this is the actual photograph which you have taken from one of the spacecrafts. So just to have an idea as to how things look like when you take the photograph from the spacecraft. Just wanted to show one or two. Say like this is supposed to be, I'll show you, say like a densely populated area in Bangalore. Say, here you can see if anyone has come to Bangalore, this is the rail bus stand. See, bus stand has got all these like arches, so that buses going to different areas of the city, they get into different locations. So it is almost like a number of this thing, and opposite side is the railway station. It's a very densely populated area in Bangalore. Here you can see the railway lines. It's a very, very densely populated area in Bangalore. So these are actual pictures which we obtained from the spacecraft after you get this thing. See here, you can see where is the application for all our, I was talking about a lot of remote sensing spacecraft. So we have different areas where we need to see. See, like we have a application on agriculture, forestry, water resources, disaster management. And then what are the requirement of resolutions? See, the different things, they require different types of resolution. Say if it is for this 5 to 50 meters, 150 to 50 to 150 meters, 20 to 30 meters, and for disasters management they require less. And then in some cases, and then different spectral bands are chosen depending on that. And then the repeativity. In some cases, say in agriculture, what happens is we want to know how things grow. Suppose this is a particular season before the Kharif season or this season comes, they want to know how things have grown and then they want to predict. In one case they will predict, in another case they will also like to know how exactly it has happened. So you require certain amount of repeativity for different applications. So agriculture requires repeativity quite fast. Similarly, forestry is not that much. And some cases, specifically in some particular cases, require for a quicker one. So depending on the repeativity, the spectral bands, and then the resolution, all those things together, the mission is decided.
IRS-1A, the first operational remote sensing satellite of India.
This is the first remote sensing satellite which was made by us, and this had it was at the 904 kilometers orbit with this one, and it carried two such cameras. One was having a 36.5 meter resolution. Then slowly we moved to this is a similar one. I don't want to see how the cameras look like. This is all done by our Space Application Center in Ahmedabad. This is full lens assembly plus this one. Total payload is done by them. It's a very intricate system, which because you can imagine the way the photographs come from such a long distance. So it is a very important, just to show us what is its actual application. All this data from this are only collected and sent through the X-band data transmission, which I was indicating to you. Just to give an idea.
This is the imagery of a part of a university as made by NIS2 camera. This is a NIS2 imagery of Malagiri in Odisha. We are seeing here the second generation satellite IRS-1C. This is a pan-chromatic camera flown in IRS-1C 1D satellites.
See here what happens in this camera, there is a small way we can rotate, there is a, so that we can view different directions and all those. This is a very good application. See, this is only to see if you want to see the same area from different this one, no? So how we can see. So in this case, on the same satellite, we have to see the same area for a longer time, then it requires to be maneuvered. So that's what we call the step and stare techniques. You stare the same area for a number of times, so you will get very good resolution from that. These are all some techniques which we use. I go.
You are seeing here part of movement as viewed by IRS-1C pan camera.
These are the views which you get.
This is the imagery of Tuticorin harbor as viewed by IRS-1D pan camera. This is an imagery of a pan camera as viewed by IRS-1D pan camera.
This is the Osmania Ministry.
You are seeing here part of Tehran.
See, we also image in other places depending on the requirement. I will go faster now.
You are seeing here
Depending on the bands you use, the coloring is done.
as viewed by TAN and LIS3 combined. We are seeing here India and Sri Lanka as viewed by IRS-1D bricks.
See, like this, we take the photograph for various things and finally construct the map. So when you construct the map, you got like that.
We are seeing
You
here
see the full
India and Sri Lanka
white field sensor immediately is constructed for India. And this is given to the user agency. User agency can be anybody in government of India. There are so many user agencies who want maps for various other reasons. So this is constructed and then
This is IRS-P3 satellite, which also had a German payload called MOS.
see here you can see that the S-band data transmitting antenna which I showed that was used here.
This is IRS-P4, the first Indian satellite for ocean applications.
See here the ocean application here. This is called the MSMR for, that is microwave remote sensing microwave payload for finding the sea surface temperature. So this also carried another one called OCM, that is ocean color monitor, where you can find out the chlorophyll content and others on the sea. And the western zone, mainly it was used much more on the western zone, where they can find out the chlorophyll content, and then based on that the fish catching can be done. So they used to have a broadcast based on the prediction which you used to get through the maps.
This is OCM camera, flown in air P4 developed by SAC Ahmedabad.
So this is almost completed. This particular P4 satellite is nearly completing 10 years. So now we are going to change over to another OceanSat 2.
Here you see microwave radiometer payload developed by SAC Ahmedabad.
This is an image of suspended sediments around Orissa coast after cyclone. Here you see the monthly average water vapor content mapped using MSMR camera.
So these are all having applications to various. So depending on
surface temperature measured by
once
MSMR.
the SSI, the sea surface temperature is measured, and once you give this, there are application agencies who will use those pictures.
We are seeing here Sundarbans area as viewed by IRS-1D WIFS camera.
See, from parts of Delhi through wires will be this one, you can see. I think this must be the Connaught place, if I am not wrong. Isn't it? These are various views which you get from the spacecraft depending on the. So this is the one more this thing now. Recently now we have been developing this satellite. Yesterday you must have heard about the SAR antenna from Mr. Raji Jyoti, that synthetic aperture radar. This is synthetic aperture radar which is going. This is a solar panel. This is full spacecraft. Is getting ready. This will be launched this year. See, the earlier ones, what we used to see is all optical imaging. From optical imaging, optical imaging has got a great disadvantage that during cloud cover and other things you cannot image. Whereas in microwave payload, that problem is not that. Irrespective of the weather, we can always have the pictures done. So this is a radar using satellite. This is a camera, one of the. This is the OceanSat 2 spacecraft, which is going to be flown in another 2 months' time. Here everything is there. Here we have the OCM, the ocean color monitor. Along with that, we have a scatterometer wherever it gives us the wind direction that is going to be flown shortly. This will also have one Italian space agency is giving another payload that will also be fixed. That is meant for this thing is called ROSA. The payload is called ROSA is meant for studying occultation on this one by using GPS. This is the Cartosat 2 for which I showed the launch. See how we can do imaging. See, depending on this one, that from Cartosat 2, we can do imaging. You can do a spot imaging, or you can do a imaging depending on the paintbrush mode, or you can have multi-view mode. Various types of imaging is possible. So depending on that, the spacecraft has to take various orientations. So that time if the antenna is a fixed antenna, nothing can do. So there we used a phaser antenna, active phaser array. See, this will be viewing. We don't know whether the mission is going to be in this mode, spot scene mode, or it is going to be in paintbrush mode, or it is going to be multi-view mode. We don't know. Depending on the necessity, they will do various things. At every time they do, we must have a real-time transmission also. So how do we do it? Unless you have an active phased array, so it cannot be done. So that is why it is known to. So this is all to get into insight as to why we are doing such a thing. See, when you do, we must also know what is the application, why they are asking us to do so that we will get to know more, and then we should be able to appreciate others' problem and try and improve it better. When you are making a system, it should be made better. So this is only this thing of that. This is only to show what are various sensors and what sort of this thing is. Say what is the mission, which mission has used what, and what are the spectral bands, what is the data rate. Say data rate 5.2, 10.4, 42.5, 105, 85, 105, 105. So that is how the various data rates we had.